Hello and welcome to this Revision Monkey video on what's going to be in the Combined Physics Paper 2 exam. This is for pupils studying the AQA specification and is for foundation tier pupils. As you are all probably aware, you do not need to recall the physics equations. This is what the equation sheet will look like, and it will have all of the equations on there for you. You will need to use the physics datasheet with the equations on to write down certain equations. For example, this says write down the equation that links force, mass and acceleration. So you'd look for the words force, mass and acceleration on the datasheet and write down the correct equation. In the calculations, for 2 marks, you would be expected to substitute numbers into the equation, so basically swapping the words for numbers. So if you had a question such as calculate the force needed to accelerate a 10 kilogram ball at 2 meters per second squared, you would write the equation down first of all, then write the numbers in that you're given. So you're given a mass of 10 and an acceleration of 2. So you just put those numbers in the equation. Mass was 10 and acceleration was 2. And then put that through the calculator and give your answer. So those ones will be 2 marks. If you see a 3-mark question, then expect either that it needs a rearrangement, or you have to include units or conversion needed, for example, nano, micro, milli, kilo, mega, giga, that you would have to convert first of all, or that you need to give your answer in significant figures. Now, occasionally they'll give you a 2-marker and expect you to rearrange it, but normally they give you an extra mark for rearranging the equation. There's much more detail on these in Physics Paper 1 and how to do these, but I'll assume that you've watched that and then we'll move on to the required practicals. So let's have a look at the units that you would need to remember for Physics Paper 2. So you might want to pause the video, have a look at those quantities and see if you can remember the units. So well done if you remember force is newtons, capital N, and weight is an example of a force, so that's newtons as well. Mass is kilograms, so that's the only thing that if you see the killi there, leave it well alone, because kilograms is the standard unit. So you don't have to convert this quantity. If you see killi there, just leave it there. Extension or distance is in meters, energy in joules, pressure in pascals, area in meters squared, velocity in meters per second, acceleration meters per second squared, wavelength is in meters, frequency in hertz, and wave speed in meters per second. Now I've left out a few units because these are ones that can be calculated by using the equations. The first one is gravitational field strength. If you use the equation weight equals mass times gravity and rearrange that to make gravitational field strength equals weight divided by mass, there you get your units, because newtons divided by kilograms will then be the units for gravitational field strength. Force equals spring constant multiplied by extension in meters. Rearrange that for spring constant equals force divided by extension, and you end up with the units for spring constant being newtons per meter, because you've done force in newtons divided by meters. The required practicals for this paper include the acceleration practical, looking into the F equals ma equation using a trolley, the springs practical, investigating Hooke's law, the waves practical, including waves in a ripple tank and waves on a string, and the infrared radiation practical with the Leslie's cube.
Investigating springs required practical. In this practical, you're going to see how the force applied to a spring affects the extension of a spring. First of all, you need to secure a clamp stand to the table using a G-clamp. This is because you're going to put lots of weights on the bottom of the spring and you don't want it to topple over. You then attach a clamp to the clamp stand and hang a spring from the clamp, like so, and attach a meter ruler to another clamp stand and measure the original length of the spring. Then attach a 1 Newton mass to the bottom of the spring and record the new length of the spring. Calculate the extension of the spring by subtracting the original length from the length after 1 Newton was applied. So our extension is going to be the difference between the original length and the new length. So this here is going to be our extension. We then add another Newton weight to the spring, so you have 2 newtons in total now as the force being applied to the spring, and we measure the new length of the spring and again calculate the extension by subtracting the original length of the spring. We then repeat it for the following weights. So we keep adding weights to the bottom and we'd use 3 newtons, 4 newtons and 5 newtons, for example, on the bottom of our spring. So each time we are changing the force, and this is going to be our independent variable, and we are calculating the extension, which is our dependent variable. And for our control variable, we need to make sure we're using the same spring each time because it must have the same stiffness. So with our results of force and extension, we should then plot force against extension on a graph. And you will see a relationship that looks a little bit like this. Any straight line relationship that goes through zero is a directly proportional relationship. So force applied is directly proportional to extension. So looking at the graph in more detail, this links to an equation which says that force equals spring constant times extension, F equals KE. So if you wanted to calculate spring constant from your values, you would rearrange that equation so that you would have K equals F divided by E. And if you do that, you can see that by calculating the gradient of the graph, so by drawing on a triangle and calculating the change in Y divided by the change in X, essentially you're doing force divided by extension so you can calculate the spring constant. That is why it's important to have force on your y-axis and extension on your x-axis. Otherwise, you'd have to do 1 divided by the gradient to get your spring constant if you had the axes the other way round. So if you plotted it with extension against force, you'd have to do 1 divided by the gradient to actually get your spring constant. So it's better to do it this way round. Hooke's law then states that for an elastic object, extension is directly proportional to force. And what it means by an elastic object is an object that will return to its original shape after being stretched. So through all of the forces that are applied here, the spring is obeying Hooke's law because force is directly proportional to extension. However, if you keep applying more force, eventually you will reach the limit of proportionality. And this is the point whereby the spring no longer obeys Hooke's law and it is the point where it stops being directly proportional. And you can see the graph curves off here. So at this point you've added too much force on the bottom of the spring and it is now inelastic. It won't return to its original shape. So your spring will just be overstretched like so with all the masses on the bottom, and if you remove the masses, it won't return to its original shape. Investigating acceleration required practical. So for this practical, we're going to need the equation that links force, mass and acceleration, and that's our F equals ma equation. Force in newtons equals mass in kilograms multiplied by acceleration in meters per second squared. So in essence, for this practical, if we're investigating acceleration, this is what we need to measure. This is going to be our dependent variable. And we could either investigate how force affects acceleration and make this our independent variable, or we can investigate how mass affects acceleration and make the mass our independent variable. So I'll talk you through both practicals now. First of all, let's discuss how we are going to measure acceleration, because that is our dependent variable. So remembering the equation for acceleration will help with your understanding with this part. The acceleration equation is acceleration equals the change in speed over time. So we've got a final velocity, an initial velocity divided by time to give us our acceleration. In this practical, to measure acceleration, we are going to use a light gate. And our light gate is attached to a data logger, which is then attached to a computer. So it can record the acceleration for us automatically. In our practical, we have an object like a trolley which is pulled along by a piece of string. Now, in order to measure the acceleration of the object, we must have this shaped card on top of our object. So the reason why it has to be this shaped is because you need 2 pieces of card going through the light gate so it can measure initial velocity with the first piece of card that goes through and final velocity and then calculate acceleration. So what we need to do is we need to measure the width of these 2 pieces of card and put that information into our data logger so it knows the width of card that's travelling through the light gate. That will then automatically calculate the speed of the card going through, and it will do the difference in the speed or velocity over time to give us a calculation of acceleration, and all of that will be done automatically. We are going to discuss how to set up the full practical in just a minute, but to calculate the acceleration part of it, we're using string to pull the trolley through the light gate, which will automatically record acceleration for us. The diagram below shows the rest of the equipment that we need to set up for the practical. Here's the light gate that we just said previously is going to measure our acceleration. We've got a trolley or a moving object with our specially shaped piece of card on top that is going to go through the light gate and measure our acceleration. To pull the trolley along, we've got a piece of string which goes round a pulley, and it has a hook with some masses on the end. Now this part of the system is just a group of objects, so we'll call the whole thing a system. This part of the system is applying the force. So we said previously, we could either change the force and investigate how force affects acceleration, or we could change the mass. Now, if we want to change the force applied to the trolley, we need to change this part of the system here, because these masses here are applying a downwards force which is accelerating the trolley. So for force, we would change this part of the system. If we wanted to change the mass of the system, we would be changing the mass of the trolley over here on this section. So shortly I'm going to go through two practicals, one whereby you change the mass and keep the force the same, and one whereby you change the force and keep the mass the same. But each of them you're measuring acceleration using the light gate. Now you'll notice I've put the trolley here on an air track. You might not have that in the exam, they might just be talking about it on a table. However, the air track is really good because it reduces friction. So if they don't use an air track, you could talk about this as an improvement to the method. So let's first look at the practical whereby we change the mass of the system but keep the force constant. In this practical, we are going to keep the weight on the hook, the force which we're applying over here. We're going to keep that constant, so we're not going to change anything about this part of the system. We'll place the trolley at the start of the air track, and we must make sure we've got the same starting position each time. So this is going to be a control variable, the same starting position. We then let go of the trolley and measure the acceleration using the light gate, and that will give us our first reading. Because we need to change this part of the system if we want to investigate how mass affects acceleration, this is where we're going to change the mass of the trolley. So you can see here I've added one mass to the back, and then we're going to repeat the process. So return the trolley to the start position and add a 100 gram mass to the trolley. Release the trolley and measure acceleration using the light gate. So we then repeat this using the following masses on the trolley, so 200 grams, and then 300 grams, and then 400 grams, and we'd use 500 grams as well. And we then repeat the experiment 3 times and calculate a mean acceleration for each mass. So that's our practical when we want to see how mass affects acceleration and when we use mass as our independent variable. Now we'll look at how force affects acceleration. So for this practical, we're going to change the force which we apply to the system, but this one's slightly different because we need to keep the mass of the whole system the same. Every time we change this, we have to place a mass over here. And the reason for that is to keep the mass of the whole system the same so that we're not actually changing mass, so we're keeping mass constant. A little bit of a difficult concept to understand, but in the exam they'll expect you to write about moving the masses from here to here. So we keep the mass of the system constant, and this time change the force, so the weight acting on the pulley. So we'll start with no masses on the trolley and 5 newtons on the hook attached to the string. Now it doesn't have to be 5 newtons, that's just a random example that I've given. You may well be using much smaller masses and therefore using a much smaller force to pull this down, but let's just say we're starting with 5 newtons on the string. We're then going to release the trolley from the starting position and calculate the acceleration using the light gate. And then to change the force applied, remove a mass from the hook down here and place it on the trolley. And that's because I said, as before, because the total mass of the system must remain constant. So you can see here I've removed one of the masses from down here and placed it onto the trolley instead. And then we do exactly the same thing, let the trolley go from the starting position and measure acceleration using the light gate. We'd repeat by moving another mass from the hook and placing it on the trolley so that the force is now 3 newtons that we're pulling down with, and again measuring acceleration. And then we'd repeat it for the following forces, so perhaps 2 newtons, moving them up here, and then we'd do it again with 1 newton as well. We'd repeat 3 times for each force applied and calculate a mean acceleration for each force. So in your exam, look very carefully to see whether they want you to change force or whether they want you to change mass, because the practicals are slightly different, but both of them you're measuring acceleration using the light gate. Investigating wave properties required practical. In this practical, we're going to use the equation V equals F lambda. So the V stands for wave speed, F for frequency, and wavelength. Now, a lot of the times you'll be asked to calculate wave speed, and to do so you will need to know the frequency and the wavelength of the wave. But you may well have a situation where you have to rearrange this equation to perhaps calculate frequency or wavelength instead. So there's two practicals that you might need to do to measure wave speed. And the first one that we'll look at is waves on a string. For this practical, we set up a piece of string on a vibration transducer and pull it tight using masses and a pulley. So you can see the wave forming here, but before we turn on the signal generator, you will just have a tight piece of string like that, which is being kept tight by the masses here, which are providing a downwards force. Now the signal generator is connected to the vibration transducer, and when you turn that on, this will vibrate up and down, so it will oscillate vertically up and down and will produce a wave, like so. We need to turn on the signal generator and set the frequency so you can see a wave clearly. So if it's oscillating up and down at a frequency where you can't see a clear wave, you're going to have to tune it on the signal generator until you see a nice clear wave forming. We then measure the wavelength using a ruler. It is more accurate to measure several wavelengths, then divide by the number of wavelengths you have measured. So this would show one complete wavelength where it goes up, down and back again to the same position. That would be one wavelength. So you could well get a ruler and just measure one wavelength like so. But to increase the accuracy, you could measure a bigger distance and divide by the number of wavelengths there are. So for example, we could measure the complete distance from here to here using a ruler and work out how many wavelengths that is. So we've got 1, 2, 3 and a half wavelengths. So if we divide them by 3.5 wavelengths, that will give us a much more accurate measurement of one wavelength. We then use the equation V equals F lambda to calculate wave speed. So wave speed equals the frequency, which you get from the signal generator because you've set that yourself. So let's say, for example, it could be 20 hertz. And then you would multiply that by the length of one wave to calculate wave speed. Another way in which you can calculate wave speed is using a ripple tank. So you'd set up a ripple tank with a shallow tray of water. Adjust the signal generator to a frequency that shows clear waves in the water. The dipper, which is just here, will then oscillate at the set frequency and create waves. So the dipper will move up and down vertically in the water, creating waves in the water. We need to adjust the frequency of the strobe light here until a clear pattern of wavefronts is seen on the screen. So you'll have a screen or a piece of paper underneath whereby you're going to see the shadows created by the wavefronts. And if we imagine a water wave, which is a transverse wave going like that, the wavefronts you're seeing are the peaks of the waves like so. And to measure wavelength, we can simply measure the distance between two of those wavefronts, and that will give us one wavelength. But again, like the previous example, it would be more accurate if we measured a bigger distance and divided by the number of wavelengths we had. So we'd use a ruler, measure the lengths of say 10 waves. I don't have 10 on the screen, but in your exam they'll probably give you one with many more wavelengths than this. And then we divide by 10 to get the length of one wavelength. Again, we use the equation V equals F lambda to calculate wave speed, and we're getting our frequency from the signal generator that we've set at a very particular frequency, which incidentally will be the same as the strobe light, because to get a clear pattern on the screen they have to match in frequency. And then the wavelength we're going to get by measuring several wavefronts and then dividing by the number of wavelengths that we've got. Infrared radiation required practical. There's two practicals that we could look at for infrared radiation. The first one is to do with emitting infrared radiation, and the second one is to do with absorbing infrared radiation. So in this first practical, we'd place a Leslie's cube on a heat-proof mat and fill it with boiling water from the kettle. Now the Leslie's cube is just a metal cube with different coloured surfaces on the vertical sides. So for example, you could have a white surface like this, you could have a matte black surface, a shiny black surface, and a silver surface, for example. Using a ruler, we would measure a set distance, so I've just suggested 15 centimetres, from one side of the Leslie's cube and place an infrared thermometer here facing the cube. We'd repeat for the other three faces, making sure that the thermometer is always 15 centimetres away from the cube. This will detect the amount of infrared radiation that is emitted by each side of the Leslie's cube. You would then repeat the experiment 3 times and calculate a mean for each side. The surfaces, such as matte black, which are really good emitters of infrared radiation, should give you really high readings of infrared radiation coming off of the Leslie's cube, whereas surfaces such as white and silver, which are poor emitters, will have lower readings. Alternatively, you could be asked about the absorption of infrared radiation instead of emission. And in this practical, you would stick something metal, like a coin, to different surfaces for example black paper and white paper, using wax. You would then put the surfaces equal distance from a Bunsen burner, so you'd measure with a ruler to make sure that they were exactly the same distance away, and this would be our control variable, the distance between the Bunsen burner and the material. And you would time how long it takes for the coins to fall. And then you'd repeat the experiment 3 times and calculate a mean. So the materials that are better at absorbing infrared radiation, like matte black, it is not only a good emitter of radiation, but if you are a good emitter, you are also a good absorber. So this material should absorb the infrared radiation that's coming from the Bunsen burner a lot quicker, causing the wax to melt and the coin to drop quicker than, for example, a white surface.
Let's first look at the difference between scalar and vector quantities. Some examples of scalar quantities are speed, distance, and time. And some examples of vector quantities are velocity, displacement, force, acceleration, and momentum. Now, the difference between the two is that scalar quantities have magnitude only. So magnitude is size. So you can give one of these quantities a big value or a small value, and that will be changing their size. So, for example, a speed of somebody could be 5 meters per second. That's giving the size of the speed or the magnitude. Somebody could walk a distance of 10 meters, for example, and that's the size that you give it. Whereas a vector quantity has both magnitude, so the size, and direction. Velocity is the vector quantity which is related to speed. So you'd give, rather than just giving a size like 5 meters per second, you'd also give some indication of direction. So you could say to the right, or in physics sometimes you'll see that they'll put a plus or a minus in front of the velocity as they've given a plus or minus to a certain direction. So if they've decided that everything moving to the right is a plus and everything moving to the left is a minus, they can put that plus or minus in front to indicate the velocity. Displacement is the vector version of distance, and you'll also have force, acceleration, and momentum that are examples of vectors as well. So moving on to forces then, we said it's a vector, so we can use arrows to show both the size of the force and the direction of the force as well. So for example, with this falling tennis ball, it will have air resistance going upwards, represented by this arrow, and weight acting downwards, represented by this arrow. The direction of the arrow shows the direction of the force, and the size of the arrow shows the magnitude of the force. So we can group forces into contact and non-contact forces. So some contact forces include friction, air resistance, tension, and the normal contact force. And in these cases, all the objects have to be touching. So friction is when 2 objects are rubbed together. Air resistance, you've got the air particles colliding into an object. Tension, you'll experience that when you pull 2 different ends of material like a rope. And a normal contact force is a contact which is acting at the normal, which is at 90 degrees to the object, which is touching another object. So for example, a book on a table would experience a normal contact force at 90 degrees from the table. Some non-contact forces include gravitational force, electrostatic force, and magnetic force. And in all these cases, the objects are separated and don't have to be touching in order to experience the force. Some forces can be measured using a Newton meter, and forces are measured in newtons. So this is a Newton meter. You could, for example, hang your object on the end of this hook here, and that will let you know the weight of the object in newtons, or you could use this Newton meter to pull or push an object and measure forces in that way. Let's have a look at this example. We've got a diver diving off the diving board, and we've got a gravitational force pulling that diver down towards Earth, or we can actually call this weight, because weight is equal to mass multiplied by gravitational field strength. Weight is a force, and it's measured therefore in newtons. Mass is measured in kilograms, so if you ever see it in grams, you would have to convert it to kilograms by dividing by 1,000. And gravitational field strength is measured in newtons per kilogram. The weight acts at a single point known as the centre of mass of an object. So here, for example, in this person, this could be the centre of mass of that person. It's quite difficult to work out for irregular shaped objects where the centre of mass is, but that's where the weight will be acting downwards. On Earth, the gravitational field strength is 9.8 newtons per kilogram, sometimes round up to 10. What is the weight of the diver if he has a mass of 50 kilograms? Well, weight is mass times gravitational field strength. So if we do the mass times by 9.8, we'll get a weight of 490 newtons. Let's look at an example if this diver was on the moon. On the moon, the gravitational field strength is just 1.6 newtons per kilogram. What is the weight of the diver if he has a mass of 50 kilograms? Well, importantly, the mass does not change. Mass is still 50 kilograms, but if we multiply it by 1.6, the diver would have a weight much less of just 80 newtons. So the key thing is your mass, wherever you are, does not change. However, your weight, because in physics weight is a force, we're not talking about mass in kilograms. When we're talking about weight in physics, we're talking about a force in newtons. So really it's important to say that your mass, you're talking about your mass when you step onto some scales, rather than your weight, because in physics weight is the force with which you're pulled towards an object. So that's why on the moon your steps will be a lot lighter and a lot bouncier, because there's less of a gravitational field strength pulling you towards the moon compared to the Earth. So important, mass stays the same wherever you are, but your weight can change depending on the gravitational field strength of the planet you are on. Looking at resultant force, then you can think of the resultant force as the overall force acting on an object. So when you take into account lots of different forces, what's the overall force? So if we look at this block here, we have 5 newtons pulling to the right and 2 newtons pulling to the left. So the 2 newtons pulling to the left, we need to take away from the 5 newtons on the right, and we would have an overall force of 3 newtons. And because force is a vector, we'd have to tell the examiner the direction that that box will move in as well. Because there's more newtons pulling it to the right, overall it would be pulled to the right. You might also get an example where there's multiple forces acting on an object. For example, if it's still 5 newtons pulling to the right, but in this case we've got 2 newtons and 3 newtons to the left. Overall on this side there'll be 5 newtons pulling it to the left and 5 newtons to the right. So 5 minus 5 would be 0 newtons. So when there's 0 newtons, there is no resultant force, or it's better to say no overall force, and the resultant force is 0. In this topic, we need to distinguish between scalar and vector quantities, and the two we're going to focus on are speed and velocity. So the scalar quantity speed has magnitude only, which means it only comes with a size, whereas velocity is classed as a vector because velocity tells you both the size and direction of movement. So for example, with speed, if an object was moving to the right at 3 meters per second, we would just class the speed of the object as 3 meters per second. However, with velocity, we need to indicate the direction that the object is moving in. So what they do in physics is they state which direction is positive and which direction is negative. So for example, a scientist could say, right, let's say that everything moving right is positive and everything moving left is negative. So rather than just writing 3 meters per second, if an object was moving to the right, when we talk about velocity, we'd have to be talking about plus 3 meters per second. So this here just indicates the direction that the object's moving in, hence taking into account direction as well as size. If the object was moving in the opposite direction, then at that same speed, we would then be saying it would be minus 3 meters per second to show it's moving in the opposite direction. So they are both very similar things. They're to do with how quickly an object moves. However, speed just takes into account the size, whereas velocity takes into account direction as well. And then there's another pairing to look at, which are distance and displacement. Displacement is the vector version of distance. Let's have a look at an example. If we have a starting point and an object moves 5 meters and then another 5 meters, the total distance would be 10 meters, 5 plus 5 making 10. However, if we look at the same scenario with displacement, with an object moving 5 meters and moving another 5 meters, because it's returning back to the same original starting point, we would actually say that there was a displacement of 0 meters because they've gone up and come back to this same starting position. So therefore its displacement is 0. So that's the difference between the scalar and vector quantities, speed versus velocity, and distance versus displacement. You need to learn some typical speeds off by heart, so I suggest writing these down, having them on some revision cards to learn them. And these are walking, 1.5 meters per second, running, 3 meters per second, cycling, 6 meters per second. So if you remember walking, running, cycling, each time these are doubling up. These are typical speeds. And then you also need to know for some other modes of transport, which is a car, 25 meters per second, a train, 30 meters per second, and an aeroplane, 250 meters per second. So when they talk about a scenario, for example, a car travelling, and they want you to do some mathematics with that, they might ask you to estimate something about the motion of that car. And if they do, and they haven't given you a speed, then you should be using this typical speed for a car. And the same if they talk about an incident involving, for example, the momentum of a cyclist, and they're talking about estimating momentum. Well, think that the typical speed of cycling is 6 meters per second. So these are just some facts to remember. A couple of other little facts then. Firstly, that the speed of sound is 330 meters per second. And also they just want you to have an understanding that the speed of wind varies. Okay, so sometimes it might be really fast wind, sometimes it would be really slow wind, as you probably know, but that's just one thing that they might ask you to apply your understanding of in the exam. Let's look at some speed equations then. This question says a bee flies at a speed of 10 meters per second for 40 seconds. How far does it travel? So this is applying the equation distance travelled equals speed times time. Distance travelled is measured in meters, speed is measured in meters per second, and time is measured in seconds. So for us to calculate this, we would do 10 times 40, which would give us 400 meters. With distance time graphs, you need to be very careful that the y-axis says distance and not velocity, and it'll always be over time. So a straight line at an angle, like this one here, shows that an object is moving at constant speed. A straight line that is horizontal shows that the object is stationary, and here again we would have another constant speed. This line here is much steeper than the third line over here, so it shows that it's moving at a faster speed. It's travelling more distance in a certain amount of time, and this one here, a lot shallower gradient, which means it is travelling at a slower speed. You can calculate average speed on a motion graph using the following equation: speed equals distance over time, which is just rearranging that distance travelled equals speed times time equation. If you want to calculate the average speed in the first 10 seconds, you draw a line from 10 up to your graph and then across and read off your distance that it had travelled in 10 seconds. So we know here that within that first 10 seconds it's travelled 40 metres, so if we do 40 divided by 10, we'll get a speed of 4 meters per second. A curved line that gets steeper shows that an object is accelerating, and a curved line that gets shallower shows that an object is decelerating. Velocity time graphs. With velocity time graphs, you need to check that the y-axis says velocity and not distance, because that's a different motion graph. With velocity time graphs, a straight line at an angle would show a constant acceleration. A flat line here would show a constant velocity because it's not moving above 40 meters per second in this case. A straight line going downwards at an angle would show constant deceleration. And then here we've got another straight line at a different velocity, so that again shows another constant velocity. You can calculate acceleration on a velocity time graph by calculating the gradient. So essentially we're using the equation acceleration is the change in velocity over time, where v is the final velocity and u is the initial velocity. You'll remember that one because u comes before v in the alphabet, so u is the starting one and v is the final one because that comes after. So if, for example, we said what is the acceleration in the first 10 seconds, we would calculate the gradient of this line here. So we'd have a look and we'd see that we have a velocity change from 0 to 40 in that 10 seconds. So 40, take away 0, so that's your final minus your initial, divided by 10, which is your time, should give us the acceleration. So acceleration in this case would be 4 meters per second squared, and have a look at the units for acceleration there. So let's consider the motion of this skydiver who's just jumped out of a plane. All objects falling towards the Earth will be accelerating at 9.8 meters per second squared. So this skydiver will have the force of weight accelerating him towards the Earth, and as he initially jumps out of the plane, he'll also have a very small air resistance acting in the opposite direction, which is shown by a smaller arrow. So here we've got a scenario where weight is larger than air resistance, and therefore the motion will be acceleration, so he's accelerating towards the Earth. And then as speed increases, so as he accelerates, then air resistance will also increase until you get to a point where the air resistance will balance out the weight, shown by the same size arrows here, and in this case he will be not accelerating anymore, but he would have reached a constant speed. And when he's falling, because he's falling through a fluid, we call this constant speed a terminal velocity. So fluids are liquids and airs, and air, if you are falling through a liquid or a gas like air, then you are said to reach a terminal velocity, which is your final velocity. You can't go any faster than that at the point that your weight matches the air resistance, is balanced by the air resistance. So then the parachutist will deploy a parachute, and at this point there is a much larger air resistance and a smaller weight, which will cause a deceleration. And then finally, the air resistance and the weight will balance each other out again, because he'll slow down and air resistance will decrease. So those two will balance out again, and he will reach a new constant speed, and therefore, because he's falling, a new terminal velocity. Forces, accelerations, and Newton's laws of motion. Let's have a look at Newton's first law. This is all to do with the resultant forces acting on an object. And the first part of it says that if the resultant force acting on an object is 0, and the object is stationary, then it remains stationary. So for this vehicle here, you've got the weight acting downwards, a normal contact force acting upwards. There's no air resistance or thrust here, so these two forces are balanced. The object is stationary, and there's no resultant force, which means it's just going to stay stationary. In the second example, if the resultant force acting on an object is 0 and the object is moving, the object continues to move at the same speed and in the same direction. So the object continues to move at the same velocity. So because velocity takes into account speed and direction, if the resultant force of this car is 0, because here we've got your normal contact force, your weight, and the thrust and the air resistance are balanced out, this car is moving and it has no resultant force, then the object will continue to move at the same velocity. So have a look very carefully to see whether the object is already stationary or whether it's already moving. Because if it's stationary and there's no resultant force, it will stay stationary. If the object's moving and there's no resultant force, it will just continue to move at the same velocity. The velocity of an object, so taking into account the size of the speed or the direction of the object, will only change if there is a resultant force acting on the object. So let's say we increased this thrust here, so we had a greater forward force compared to our air resistance. Now we have unbalanced forces. We will have a resultant force overall acting in this direction here because of this increased thrust. And then now we'll be changing velocity. We'll be changing the speed, not necessarily the direction, but the speed of the object as it will accelerate forwards. Newton's second law says the acceleration of an object is proportional to the resultant force acting on an object and inversely proportional to the mass of an object. This links to the equation F equals ma, or force equals mass times acceleration. Force is measured in newtons, mass in kilograms, and acceleration in meters per second square. So look out for this symbol here. This shows that acceleration is proportional to the force, and you might also see it in a sketch graph of acceleration against force as well. So for example, if we had force and acceleration, they would be directly proportional. And this means as force increases, acceleration increases. And in the other relationship, acceleration is inversely proportional to mass. And this means as mass increases, acceleration decreases. So inverse proportion means as one thing gets bigger, the other thing gets smaller. And that's where you'll see A graph, if we put mass against acceleration, would look a little bit like this. As mass increases, acceleration decreases. Let's have a look at an example. A boy kicked a 500-gram stationary ball with a force of 20 newtons. Calculate the acceleration of the ball. Well, first of all, let's look at converting the grams into kilograms. So 500 divided by 1,000 would give you 0.5 kilograms. So do look out for those kind of things in the exam. The equation we're using is force equals mass times acceleration. That's one that links to Newton's second law. And we'll put the numbers in that we've got. So 20 newtons is the force, 0.5 kilograms is the mass. So if we rearrange this, acceleration would be equal to 20 divided by 0.5, which will give us an acceleration of 40 meters per second squared. Newton's third law says that whenever two objects interact, they have to be two different objects. Whenever two different objects interact, the forces they exert on each other are equal and opposite. So this is that equal and opposite law. So for example, when you sit this mug on a table, the mug will exert a force on the table, and the table will exert a force on the mug that is equal in size and opposite in direction. When you press this button here, one object is the finger, the other object is the button. The finger will press the button with a force and apply a force to the button, and the button will apply a force in the opposite direction that is equal in size and, as I said, opposite in direction. Forces and braking. Let's first of all look at stopping distance, which is made up of thinking distance, which is the distance the vehicle travelled during the driver's reaction time. So this could be a definition that you're asked to write. Don't forget it's got the word distance there. So thinking distance is not to do with time, but it's the distance travelled during the driver's reaction time. And braking distance is the distance the vehicle travelled under the braking force. So these are definitions people get wrong a lot of the time because they start to think about time rather than distance. So if we add these two together, thinking distance plus braking distance, we will get the overall stopping distance. So driver's reaction time normally falls within typical values of 0.2 and 0.9 seconds, but this can be varied by different things that we'll discuss later. So let's have a look at a scenario here. We've got a car driving along and a woman steps out. So the point then here that the driver notices the woman in the road will be the point that he starts to think about putting on the brakes. And at this point later on, this is the point where he actually applies the brakes, then this distance in between will be the thinking distance, the distance the car travels during the driver's reaction time. Because he sees the woman, but don't forget the car is still travelling, but by the time his brain has told his foot to apply the brakes, then the car will have still travelled a certain distance, which is that thinking distance. He then applies the brakes, and then the braking distance is the distance under the braking force, so it is the distance travelled between this point that he applies the brakes and this point when the vehicle finally comes to a stop. And the total distance is therefore the stopping distance, the thinking distance plus the braking distance. And importantly, if we add these up, 10 metres plus 20 metres, for example, we can calculate the overall stopping distance for the car. Thinking distance and braking distance both increase with speed, so both of these sections here are going to get longer the faster you are going. And therefore stopping distance in total increases with speed, hence why you have lower speed limits in areas where there are more pedestrians. Certain things can affect thinking distance, including tiredness, that will increase the thinking distance. Drugs, most drugs will increase the thinking distance because they'll slower your responses. Some of them may increase it if it's a stimulant as well. Some of them may decrease the thinking distance if it was a stimulant that improved your reaction time. Alcohol, that is a depressant, so that would increase the thinking distance. It would take longer for you to react to apply the brakes, and distractions as well. So all of these things can affect thinking distance, most in a negative way, which will increase the distance. And then braking distance, that's things that would affect the distance travelled under braking. So those are wet or icy roads. It would take longer to stop, therefore the braking distance would increase. The condition of the tyres, there's not enough tread on the tyres, that would affect the ability of the car to stop, and the braking distance would be longer. Condition of the brakes, again, if there's not a good thickness on those brake pads, then that will affect the ability of the car to stop. When you brake, work is done by friction between the brake and the wheel, and that's because you will apply a force against the wheel to slow the car down. So you're doing work because work done is equal to force times distance. So if you apply force over a certain distance, you are doing work. And if you remember, work done is the same as energy transferred. So when we're doing work, we are also transferring energy. And in terms of a car slowing down, the kinetic energy of the vehicle decreases and the temperature of the brakes increases. So you've got a decrease in the kinetic energy store of the vehicle and an increase in the thermal energy store of the brakes. And really large decelerations may lead to the brakes overheating and a loss of control. So you can see here bright orange glowing wheels here because the temperature of the brakes has increased so much. And the greater the speed that you are travelling, the larger the braking force that is needed to stop the car within a certain distance. So the faster you're travelling, the bigger the braking force you need to stop the car, and therefore the more likely you are to have these overheating brakes and a loss of control as well at those greater speeds.
Reaction time varies, but is usually between around 0.2 and 0.9 seconds. I'm not going to dwell on this practical because you would have done it in detail in Biology Paper 2 as a required practical, but you can use the ruler drop method to measure reaction time. So person A would drop a ruler, and then person B catches the ruler as soon as possible, and we can use a conversion chart to convert the distance that the ruler fell through the hand, this part here, into a reaction time. But if you want lots more detail on that, you can look back over the required practical that comes up in biology.
Let's have a look at some acceleration equations then. We've got A equals v minus u over t, where acceleration is in meters per second squared, final velocity in meters per second, initial velocity in meters per second, and time in seconds. So you should remember that u becomes before v in the alphabet. So u is your initial or starting velocity because that comes first, and v is your final velocity because that comes afterwards. Let's have a look at this question. A dog was sat still when he heard someone at the gate. The dog reached the gate in 2 seconds, so that is going to be our time, and was travelling at 6 meters per second when he reached the gate. So this is our final velocity. Calculate the acceleration of the dog. Calculate A. So the other bit we need is u. We need the initial velocity, so you need to read the question very carefully again. It says a dog was sat still. So this here implies that the dog was stationary, therefore that is our starting velocity, which was 0. So then we can do 6 minus 0, so v minus u, divided by the time, which is 2, and our acceleration would be 3 meters per second squared. Then we've got another acceleration equation, which is v squared minus u squared equals 2as. Again, acceleration, final velocity, initial velocity, s in this equation is distance. And let's have a look at this practice question. It says, an aeroplane accelerated at 10 meters per second squared from 100 meters per second to 200 meters per second. Calculate the distance travelled by the plane while accelerating. So this time we're rearranging this equation to calculate s. You might have to rearrange the calculation to calculate any one of u, v, or a. So let's have a look at it then. 200 squared is our final velocity here. U is our initial velocity of 100 meters per second. So we square that, and then that is equal to 2, which is our constant in our equation, multiplied by acceleration of 10, multiplied by s. So if we simplify this, we're saying that 30,000 equals 20 times s, because those two make 30,000, those two make 20. And then rearranging it to 30,000 divided by 20 equals s. So s is equal to 1,500 meters. Work done and energy transfer. When a force causes an object to move through a distance, work is done on the object. So because we're talking about distances, we can say a force does work on an object when the force causes a displacement of the object, because distance and displacement are linked. Distance is scalar and displacement is vector. So there's an equation that links work done, force and distance, and this is work done equals force times distance, where work done is measured in joules, force is measured in newtons, and distance is measured in meters. The reason why work done is measured in joules is because it's the same as energy transferred, and obviously energy is measured in joules. But you do also need to be aware of another unit for work done, and that is Newton meters. So 1 Newton metre is equal to 1 joule. And the Newton metre comes from the fact that you're multiplying a force measured in newtons by a distance measured in metres. So you might see work done in Newton metres, or you might see it in joules. So an example using the calculation calculates the work done when 20 newtons of force pushes a wooden block 25 centimetres. So the first thing we need to do is sort out these units, because we said distance needs to be in metres. So convert this to metres first of all. 25 centimetres is equal to 0.25 metres. And then put our numbers in the calculation. Work done equals the force multiplied by the distance, which would equal to 5 joules. Or, like we said in the exam, you might see it as 5 Newton metres.
Forces and elasticity.
To squash or stretch a stationary object, you need to apply it to forces that push or pull an object. So the other word for squash is to compress. So you need two forces, because otherwise if you just had one force applying against the object, that would cause the object to accelerate in the direction of force, because of force equals mass times acceleration. So if you just had one force, that object would accelerate in the direction of the force. However, if you have two forces, that can then, in this case that we're going to do, cause the object to compress, or equally, if they were pulling, you could cause the object to stretch. To stretch a spring, you need to apply two forces that pull either end of the spring. So, for example, you could have it on a clamp here, and you could add some weights to that, so you'd have the force of weight acting downwards, and then a tension force acting in the opposite direction. That is two forces, therefore applying on the string and allowing it to stretch. So there are two types of objects. There are elastic objects. Those are objects that return to their original shape after being stretched. So if you think of a spring, once you remove a weight, as long as it's not too much of a force that has stretched it, if you let go of that weight, take it off, it will return to its original shape. And in that form, it is elastic, and we could say it has been elastically deformed. So when you take off the forces that are being applied to that spring, it will return to its original shape. Inelastic is the opposite. So inelastic objects are the opposite to elastic objects. They don't return to their original shape after being stretched. So again, we would say an object in this case has been inelastically deformed, and there's no chance of getting that to return to its original shape. Hooke's law: some elastic objects, importantly, obey, like springs, obey Hooke's law. Hooke's law states that when you double the force applied to an object, the extension of the object also doubles. And there's an equation that comes into play here, which is force is equal to spring constant times extension. Force is measured in newtons, spring constant is measured in newtons per metre, and extension is measured in metres. So force is directly proportional to extension in elastic objects. So if we were to plot force against extension, this time I've got it in centimetres, but you could also have converted it to metres. When an object is obeying Hooke's law, a graph of force against extension will show a straight line that goes through zero. Remember, this relationship is called directly proportional. Any straight line through zero is directly proportional. If the object is overstretched, it will lose its elastic properties and the graph curves off. And this point here, we'd call its elastic limit, or limit of proportionality, because that is the point that it is not proportional anymore. So here is its limit of proportionality. And at this point, it's gone beyond its elastic limit and no longer obeys Hooke's law. Work is done when a force stretches or compresses an object. And in this case, remember we're talking about two forces needing to stretch or compress objects. And energy is transferred to the elastic potential energy store of the object. So we know that work done and energy are both measured in joules, because work done is the same as energy transferred. So when you compress or stretch an elastic object, it will transfer energy to the elastic potential energy store. And this equation links our factors. We have elastic potential energy is equal to 0.5, which is a constant, that stays the same, multiplied by spring constant, multiplied by extension squared. And we measure elastic potential energy in joules, spring constant in newtons per metre, and extension in metres.
All waves transfer energy. There are two types of waves, longitudinal, and transverse. A sound wave is an example of a longitudinal wave. In a longitudinal wave, there are regions of compression and rarefaction. So here we have all the particles close together, and that's a region of compression. And next to it, where the particles are further apart, that's a region of rarefaction. In a longitudinal wave, the oscillations are parallel to the direction of energy transfer, which means the movement of the particles backwards and forwards is parallel to the direction of energy transfer. Water and light are examples of transverse waves. In a transverse wave, the oscillations are perpendicular, which means at 90 degrees, to the direction of energy transfer. So that means whilst the particles oscillate up and down, the direction of energy transfer is perpendicular. An oscilloscope can be used to view wave properties. So you've got the peak and the trough. A represents a wavelength and B represents the amplitude of the wave. So one complete wave is where you start from one point, go down and up again to the same point. So that could be one complete wave, or starting here, going up, down and up again to the same point would also be one complete wave. So you could also measure the wavelength between these 2 points, for example. That would also be wavelength, that would be same distance as you've measured over here in A. Frequency is the number of complete waves that go past a certain point per second. Frequency is measured in hertz. So wave B on the diagram has a higher frequency than wave A because more waves are passing a certain point every second. There is an equation that links to frequency, which is period equals 1 divided by frequency, and period is the time it takes for one complete wave to pass a certain point. So there's one complete wave, and period would be the time it takes for one wave to pass a certain point. So you might get a question like calculate the time period of a wave with a frequency of 20 Hertz, and you'd use the equation, put the numbers in, and then your answer would be in seconds because period is the time it takes for one complete wave to pass. The speed of sound in air is approximately 330 meters per second. So we can use the following equipment to measure the speed of sound. We've got a signal generator connected to a speaker, and we can set the signal generator to a particular frequency, for example 200 Hertz, and that means the speaker will oscillate backwards and forwards 200 times a second. Then, if we place two microphones equal distances from the speaker and connect these to an oscilloscope, we will get two different wave fronts on the oscilloscope. We'll get one for microphone 1 and another for microphone 2, and they will be identical because they are equal distances to the speaker. Then you would move one of the microphones, let's say microphone 2 for example, you would move that backwards, and as you do that the wavefront will move as well, and then it won't be identical anymore. So you'll have microphone 1 here with your complete wave, and microphone 2 would have shifted slightly to the right as you'd moved the microphone backwards. But then, if you move microphone 2 back a little bit more, you'll eventually get to the point where you have identical wavefronts again. And as you can see here, both of these traces are in exactly the same positions again. And when you do that, you can work out the wavelength of the sound wave generated by the speaker, because that is the distance between the two microphones. And you would measure that with a ruler and record that distance, for example 1.65. So now we have a frequency, which is 200, set by the signal generator, and a wavelength of 1.65, which we've measured as the distance between the two microphones when the wavefronts realign perfectly. We can then use the wave equation V equals F lambda, or wave speed equals frequency times wavelength, to calculate the speed of sound. So in this case 200 Hz as set by the signal generator multiplied by the wavelength of 1.65 gives us 330 meters per second.
Electromagnetic waves. Electromagnetic waves are transverse, and they all travel at the same speed, which is 3 times 10 to the 8 meters per second. You need to know the order of electromagnetic waves in the spectrum. So this is showing the order from the longest wavelength to the shortest wavelength. And the order will be radio waves, microwaves, infrared, visible light, ultraviolet, X-rays, and gamma rays. And this is also the order from the lowest frequency wave to the highest frequency wave. So down this end of the spectrum, you'd get the longest wavelength waves, and at this end of the spectrum, the shortest wavelength, high frequency, high energy waves. Don't be put off in the exam if they ask you to list them in the other way, from shortest wavelength to longest, from gamma through to radio waves. In the middle, the visible light is split up into red, orange, yellow, green, blue, indigo, and violet. So if you were to split what we call white light, you would see this spectrum of colours. So you need to know that order, Roy, G, Biv. And you'll see that the red is closest to the infrared light in the spectrum, and the violet is closest to the ultraviolet. And this is why lots of things emitting ultraviolet will also emit parts of the visible light spectrum, and you'll see them as violet. Things that emit infrared radiation will also often emit part of the visible light of the spectrum, so they will come through to your eyes as red. Our eyes detect only visible light. So there are lots of other waves of electromagnetic radiation, but our eyes, as an organ, only detect visible light. Some animals, for example, can see into ultraviolet light, but our eyes only see visible light. The high frequency, short wavelength, high energy end of the spectrum can have hazard effects on human body tissue. So these are UV, X-rays, and gamma rays. For example, ultraviolet light can prematurely age the skin and cause skin cancer. And it's important in the exam, if you're talking about ultraviolet, that you must link this directly to skin cancer and not just generally write cancer. X-rays and gamma rays are both ionizing. That means they can strip electrons off of atoms. So they can cause gene mutations and also cancer. And we could be a bit more general there because they can cause different forms of cancer. So these ones are particularly dangerous, and ultraviolet we should try and avoid as much as possible as well through sun creams and wearing appropriate clothing in the sunshine. Radiation dose is measured in a unit called sieverts, and it's a measure of the risk of harm resulting from radiation exposure. And it's useful in hospitals because there will be doctors and nurses and other staff members that work in areas where there are, for example, lots of X-rays or gamma rays. Or patients might need to have lots of X-rays or treatment involving gamma rays. And you need to know how the radiation dose is going to affect you and what the risk of harm is. So radiation dose takes into account two things. It takes into account the type of radiation that you're exposed to and the size of the dose that you get. Okay, so you need to bear in mind that radiation dose takes into account the type and the size of radiation that you are exposed to, but you don't have to remember that the units are sieverts. So you might see sieverts in a question when they're talking about dose, but you don't have to remember those units. So let's look at the uses of some of these electromagnetic waves. Radio waves are used for TV and radio communications. Microwaves are used for satellite communications or for cooking food. And because it's a spectrum, it will be a different wavelength used for cooking food compared to the wavelength that you would use to communicate with satellites. Infrared radiation, that's used in electrical heaters, cooking food. So both of these two will obviously glow red because it's close to the red part of the visible light spectrum as well. And also infrared cameras, which will detect infrared light rather than visible light. So the heat or infrared coming off of objects will be detected by those cameras. Visible light used for fibre optic communications. Ultraviolet light used for things such as tanning beds or energy efficient lamps using ultraviolet. X-rays, medical imaging, and gamma rays, medical treatment. So gamma rays are often used to kill cancer cells, for example. All electromagnetic waves change direction when they enter a different medium. So you can think of this as a different material. So this is called refraction. So refraction is when waves change direction when they enter a different medium. So here you've got the medium of air, and here's your barrier, and the other side you've got glass. So air and then glass. So this wave is coming in here, hitting the glass, and is bending. So rather than carrying on this same direction that it was going through first of all, it's bending and changing direction to head out this way. And if it enters a denser medium, it will bend towards the normal, which is in the case of this diagram here. So air is less dense than glass, so the wave is heading in this direction. It's going from the less dense air to the more dense glass, so it bends towards the normal. The normal is this imaginary line here, this dotted line. This is the normal line, and this is drawn at 90 degrees to the surface. So here at the boundary that it joins here, this angle here is 90 degrees, and that is the normal line, or you could draw the 90-degree angle there, either or. It is 90 degrees to the surface. So rather than carrying straight on here, you can see this is bending towards the normal, so this angle will be a lot larger than this angle here. Permanent and induced magnetism, magnetic forces and fields. Let's first of all look at permanent magnets. So permanent magnets have a north pole and a south pole, and opposite poles attract each other, so north and south here will attract, and like poles repel each other. So if you bring two south poles together, those will both repel, and if you bring north poles together, they will also repel. Magnetic elements are iron, cobalt and nickel, so there are only 3 magnetic elements. Other substances can be magnetic, for example, steel is an alloy that is magnetic, but that's because steel contains iron, and iron is a magnetic element. So you will see other substances that are magnetic, but that's because they will include one of these magnetic elements. Let's look at induced magnets. So if we were to bring 2 paper clips together, they would not attract each other, and it would fall down again. However, because paper clips, most of them are made out of a magnetic material, a lot of them are made with iron in them, then if we were to place this inside a magnetic field of a permanent bar magnet, so here's our bar magnet, if we bring our paperclip close to that, so it is within its magnetic field, then it will become temporarily magnetic, and it will then be able to attract the paperclip. So we would call this now an induced magnet. So an induced magnet becomes magnetic when it's placed in a magnetic field. An induced magnet quickly loses its magnetism when removed from a magnetic field. So after a little while, the attraction here would go away because that paperclip wouldn't be magnetic anymore, and it would simply fall away again. We can draw magnetic field lines around a permanent bar magnet. So there are invisible magnetic field lines to show the magnetic field. Magnetic field lines always point from north to south. So you can see here we've got north, so these field lines coming out here have the arrows to show they're going away from north, and the field lines on this end show they're going in towards south. And at the top here, the lines are going from north to south, shown by these arrowheads, but at the bottom, look carefully, they're also pointing left because they're going from north to south. So you'll need to be able to draw these magnetic field lines around a bar magnet like this, and draw the arrows on as well. You draw at least 2 lines above, at least 2 lines below, and a few coming out of the poles. So the closer the field lines, the stronger the magnetic field. So at the poles here, where the lines are closest together, that will be where the magnetic field is strongest, and you'll get your strongest attraction here. Looking at compasses, because they involve magnetism as well, the Earth itself has a magnetic field, and actually at the North Pole, that is where there is magnetic south, and at the South Pole, that's where there is magnetic north. A compass contains a small bar magnet, and this bar magnet here is on a frictionless surface so it can turn all the way around freely. And a compass, the north part of the compass, will point towards magnetic south. Okay, it is the North Pole, hence why we can direct ourselves around the globe using north and south. But the actual small bar magnet inside here is pointing towards magnetic south, because if you remember, in magnets, north is attracted to south. So the Earth's invisible magnetic field has a magnetic south at our North Pole. So if we put the plotting compasses around, you can see at this North Pole here, you've got the north part of the magnet being repelled and facing away, so that's going in this direction, out from the north. And at the South Pole, the north is attracted to the south, so that's going in towards the south. And then around the outside, you've got these plotting compasses here and here. So this one, again, is always going from north to south, so you can see here, going from north pole of the bar magnet towards the south, so the north part is being repelled towards away from this north and attracted towards the south. And again at the top here, this plotting compass here, the north part of this small bar magnet inside the compass is being repelled by the north pole of the permanent bar magnet and being attracted towards the south. So you'll see here the field lines will then look very similar to our normal bar magnet when the field lines are away from the north and into the south pole. The motor effect. When a current flows through a conducting wire, a magnetic field is produced around the wire. So let's have a look at the right-hand thumb rule. You can use your thumb to show the direction of current, and for example, if your thumb is pointing upwards, the direction of current will be up from positive to negative, and your fingers will show the direction of the magnetic field. So you can imagine your fingers pointing inwards like so, and importantly it has to be your right hand that you use to do this. So if you make a fist and a thumb with your right hand, the thumb would show the direction of current, so in this case we could do positive to negative, and your fingers would show the direction of the field lines. If the current is flowing in the other direction from positive to negative, you simply turn your thumb upside down and that will show you the direction of the field lines depending on where your fingers curl into your palm. So if we use that rule on this wire, you've got the wire travelling up here from positive to negative, the current would be upwards, so we could point our thumb up like shown in the diagram here, and the magnetic field lines would curl round into our palm like so. So we can draw the arrows on the field line going in that direction. The magnetic field line is stronger closest to the wire, and you can see that because the field lines are closer together, so they're stronger closer to the wire, and as they get out they would just get further apart and weaker. And if you increase the current flowing through the wire, the strength of the magnetic field also increases. A coil of wire is called a solenoid. So this would be a solenoid. And a solenoid, if it has a current flowing through it, will produce a magnetic field. So very similar to the bar magnet, you've got your north and your south, and the field lines always go from north to south. The magnetic field line inside a solenoid is strong and uniform. You can see that by these straight lines of the field lines inside. They're really close together, so the magnetic field is strong and uniform because there are straight lines of field lines going through. If you add an iron core, you increase the strength of the magnetic field. So if you put a core inside there, and a solenoid with an iron core is called an electromagnet. So if you were to put an iron core inside that coil, we could now call that an electromagnet. Electromagnets are useful because when an electromagnet is switched off, it loses its magnetism. So if we switch these off now, it would drop the nails, and this makes it useful for picking up objects and dropping them somewhere else. So for example, on a scrapyard, they're used to pick up magnetic objects and drop them somewhere else in the scrapyard.